First of all, thank you for everybody for coming today. In many respects, today is sort of a celebration for our research team because we've come a long way since 2004. And in the last 2 or 3 weeks, we've seen the wet areas mapping data gone public. And today is an opportunity to sort of kickstart the application of wet areas mapping in the energy sector. So today was a long time in coming, but we are now here. So just to start off, for my first presentation today, I'll just give you a little bit of a background as to how this got started and a little bit of a background of what wet areas mapping is. And then you'll see various presentations after mine today that go into quite more of the detail about how it's generated and some of the speakers to talk about the applications and how it works for their particular operations. I thought I would start with this particular slide, though, because it really talks to some of the themes that we've already heard today. We've heard from Shannon this morning and from Dr. Isaacs about innovation and the importance here of innovation in Alberta to deal with many of the complex land use challenges that we have, but also the need for collaboration. And so when we started this project back in about 2005, we really recognized the need for the government to work very closely with our industry partners. And our first experiment was in 2005, and it was with Miller Western Industries and a number of the other forestry companies. And it's grown considerably since that time, but every step along the way that it's grown larger and larger, it's involved more partners. We also recognized very early that we want to build on each other's knowledges and skills. And that was kind of unique for our province. We recognized that many of the challenges that we have in land use are not unique per se to Alberta all the time. We travel across Canada and other jurisdictions. They also have challenges with respect to water and land use planning, etc. And we didn't want to necessarily always reinvent the wheel here in Alberta. One of the things we were eager to do was to capture innovation in other areas and bring it here. And this was a really good example of wet areas mapping that was actually developed in New Brunswick starting about 1999 and had gone operational there and in the Northeast United States in 2003. And I saw it at a conference in 2004, and at the time we didn't try to recreate it here in Alberta, we tried to build on it. So that was the recognition of the need to build partnerships with the university. And also we're willing to take risks, and you have to in terms of innovation. I can't help but mention that when we started this in 2004, 2005, we had an awful lot of naysayers. And you know, we took those risks and we think they've paid off. But that's very important. Much of what I'll speak about today is actually work done by other people. I signed the grant agreements, I worked with graduate students, but the real work here that you're going to see is by our research partners at UNB. And in particular, it's by Jay Ogilvie. He's standing here to the left of me. Jay is our modeling guru. So any of the mapping products that you receive or work with or you see here today have all been created by Jay. He's also our guru that works with the raw LiDAR data. A lot of the work that Jay has done has been looking at different techniques on how to look at the LiDAR data. And then a subsequent group of graduate students that have tried to apply it in the field. Standing to the right is Dr. Paul Arp. He is the professor of forest soils at UNB, and he's also been extremely important to this research team. In light of noting Dr. Paul Arp, I would say that everybody in our research group is a forest soil scientist. We are not hydrologists. And this innovation was designed as a planning tool or akin more to the field of forest soil science. We're really interested in what's going on with respect to soils between stream channels, and I'll give a demonstration of that. Our partnership list has grown considerably over the years, as I mentioned. When we first started, our first investment of research funds was the Forest Resource Improvement Association of Alberta. That was in 2005. In 2006, it expanded with the involvement of the Sustainable Forest Management Network, a national center of excellence. And there's been a growing list of companies, both here in New Brunswick, that have been very integral in the development of wet areas mapping. This is a very important slide because it really highlights sort of the guiding principles or the objectives of the wet areas mapping. and they're cogs because they all work together. One of the driving factors was to reduce cost within industries in Alberta with respect to land use planning. And our belief is that if we can reduce costs within industry sectors, then that increases their competitiveness. We know particularly within the forestry sector, we've come through a period of very low wood prices, and continuing our efforts to drive down planning costs, operational costs is a key objective. We also want to be able to streamline our own efficiencies or plans within the government of Alberta. We know that we have to do far more now than we did in the past with fewer resources, and we want better outcomes. So we're always looking at opportunities to streamline for new approaches. And you'll hear some of those here today, as well from other Government of Alberta staff. Of course, one of the most important aspects here is the stewardship. And we recognized early on that it's not enough just to tell people that you have to sustain A or B. What Albertans really needed was the tools in order to do it. And that was one of the key thoughts as we went along this process, was to be able to generate a tool or an output that we could then give to Albertans and say, here, this is going to help you better plan, mitigate around the water and land interface. And then finally, this one was added more of late, was we have this huge innovation capacity within Alberta, in our innovation community, and we wanted to make sure that we had the best spatial information that was going in there to provide better output. We heard a lot about LiDAR, and the government of Alberta has been very ambitious in the purchase of a site license for LiDAR. So we don't own the LiDAR outright. We purchase a site license to use it internally. Our current inventory is around 28 million hectares. If Shannon's meeting this afternoon goes well, we'll have about just under 30 million hectares. We continue to buy LiDAR in the far north, up in this area here. We hope to purchase this afternoon. Our LiDAR is considered medium quality, but it gives us a huge opportunity to innovate. So this is an example of the wet areas mapping, and I'll show you a few examples here as we move along. This is an aerial shot. It's northwest of Peace River, and this is a large forestry experiment called EMEND. It's one of the largest forestry experiments in the boreal forest in the world. It's located right here in Alberta. And so you're looking down at a variety of clear cuts and forests, but really what's noteworthy is the hydrology layer of the province is turned on right now. And that's the data layer that companies have to manage for water sustainability and soil sustainability in the landscape. And the wet areas mapping process really tries to find out where water is on the landscape and where it's not. This is the new map for that area, so it's a dramatic difference. And if you've worked in the boreal forest, and most of you have, you'll know that there's water everywhere. And I'll go through what these codes mean in colors in a second, but the wet areas mapping is showing us everything from large stream channels all the way up to ephemeral draws. And the idea here is that what we've identified is where water is on the landscape about 2 weeks after you'd have a really heavy rain. So in essence, it is a hydrological risk model. It is static, and it's on purpose. So if you were to go out on this landscape after 4 or 5 years of drought, a lot of these wet areas that are identified would of course be dry. But this is the type of information that you actually want to plan around, because even in those dry years, it tells you where your risk is going to be. So Jay Ogilvy's talk, which will follow our break, will go into some of the detail as to how this model determines. But essentially what the model is doing is that there's about 20 different algorithms now that are used. This is the bare earth, and we see this is just the geotiff turned on. So the dark blue are wet areas where we'd say the water table is close to the surface. We've color-coded it to different depths. So the darkest is 0 to 10, the next is 10 to 25, 25 to 50, 50 to a meter, and then we turn it off. And we take a cross-section through it, and this is what the model is actually looking at. The top line is the bare earth surface, and this blue line here across is what the model is determining where it thinks that surface water table is. So on the far left, we've got a little bit of a hill. The model is telling us that surface water table is quite deep. We actually don't dig soil pits that deep, so we sort of ignore this type of data. But it's coming to the surface where we have this wetland complex. You'll actually see there's a little bump right here, which corresponds to this little dry area there. The water table drops, and it darts to the surface in a couple of spots where we have very, very small, probably very small intermittent streams. And then I'll go through some of the applications. So this in the background is the bare earth, 1 meter resolution, and the dark blue is where we would have a saturated soil, probably either a glycolic soil or an organic soil. If you put a piece of site equipment on it during the summer, it'll probably sink. And then as we move away, the depth of the water is dropping, so we'd have, this would probably is an organic, this is probably a glycolic soil, and then we get to an area that's dry. The one thing that I want to point out, though, is that all of our data is calculated using either the raw data or the highest resolution. So every square meter of the landscape has a value of what the digital elevation model is. We know the tilt of that 1 square meter, so we know the water will move from 1 square meter to the next, to the next, to the next. We know how many pixels or how many square meters flows into that square meter from above. And when we have 40,000 square meters flow to one particular point, we start a flow channel. So we found very early on in our research that if we moved from 1 meter, using 1 meter resolution to even 2 meter or a little higher, we started to lose some of the accuracy in our model. So everything that is run in our group is run at the highest resolution that we can. The trade-off is that it is an exceptionally long, timely process. So we get a lot of requests for data, and usually what we tell people is we're going to do it, but it might be another year. And the reason is because it's a very timely process. We did one FMA, forest management area, near Hinton. It was 1 million hectares. At the time, it ran for 3 months on 48 computers. And the reason is because it's 1 meter by 1 meter by 1 meter. It's a lot faster now, but it is still a matter of months and not days. And we keep that very high resolution for the quality of the output. So when we talk about wet areas, really what we're talking about are features on the landscape that are very well hidden. When the original water layer was developed, they're using aerial photos. They're often most of these features they can't see because the canopy is so dense. So we're looking at features that even when you're walking from a distance or looking at it from 20 or 30 meters away, you don't see it. When you get right on top of it, you'll see that there's stream channels going through, and even here it's hard to find. Quite often when we're out in the field validating these features, we actually don't find the small channel that might only be 10 centimeters wide, except with the uses of the GPS. But we know that when you put in a disturbance or a clear cut, all of those features suddenly come to light. And sometimes many of the wet areas at the total headwater, they start out as a series of puddles. And then as they move down through, they turn into channels. So one of the things to note is that we're not always perfect. It is a model. So there will be times where the output is wrong. The data is subject to broad assumptions. And it's never a substitute for professional judgment and due diligence. I'll leave it to others to talk about how accurate the output is. But we know that it either works with surprisingly accurate, and then sometimes it's absolutely wrong. And the times when it's wrong is usually where we have a false digital elevation model created from the LiDAR. And that doesn't happen very often, but when it does, it throws off results. And essentially what happens in some cases is the light will come down, the energy beam, and it'll hit off the top of sphagnum, usually. Or it could be a lot of stumps or wind throw. And the digital elevation model that is created is actually false. So the surface of the earth looks like it's a little bit higher than what it should be. In those particular areas, the wet areas will actually come out as dry in some cases. It's a small proportion of the land base, For forestry applications, it's a very small, it's usually the inoperable land base. As we move forward now, we've corrected for that, and I'll show you some examples. So just looking at it again, here's again a part of the northern boreal. And one of the reasons we really like this is because it changes our approach to management from going out of the landscape and looking at things to verifying. And this is a good example, and you'll hear about it a little bit more in other presentations. We've got our hydrology layer turned on to the left. If you look here, you'll see that there's buffers on some parts of the landscape. Here's a buffer. There's other buffers here. There's equipment-free zones. My point here, though, is that in order to find those, somebody with the company had to go out and spend the day walking a block to find out where water was and where water wasn't. And then they would flag out a buffer. Our department might go back out and check their work. Energy companies are walking the same landscape. In this particular area, it would be Shell. So you've got all these people are walking this landscape trying to find out where water is and where water isn't. Oops. This is the bare earth, again at 1 meter resolution. It's really neat, always look at these. And this is the wet areas mapping. It's generated, so we've got areas of the landscape that are saturated soils, a lot more stream channels, and this is what it looks like for a forestry application. And what always amazes me is that our modeling guru, 4,000 kilometers away, consistently nails these buffers and small stream channels. So we can see where somebody laid out a buffer probably 10, 12 years ago is lining up today with the wet areas mapping. Now, the reason that this is important, again, is because we're shifting from having to go to the landscape and try and find everything from scratch to now merely going out and expecting that I'm going to find this, and I might just verify that it's there, or maybe even before that I might just plan around it. And that has a big implication in terms of cost. What I would also say is that we very seldom miss a stream channel. Very, very rare. We will sometimes have, usually where it happens is a stream channel can get moved because of problems with a clear cut and a lot of stumps, but it is very seldom that we'll actually miss a stream channel that is actually there. We will have small errors with respect to saying there's one here and it might be the flow initiation point might have been further down. But it is very seldom that we see something on a map that actually isn't there in the field. Today, the scope of this project grows every year, but today we have funding to model about 20 million hectares. What is completed today is illustrated here in green, and this is the data set that is now publicly available. So it's about 14.2 million hectares, and right now we have funding to map everything here in the northwest and much of the northeast. So some key attributes, and ultimately why we really like this is because at the end of the day, while we've had 8, 10 graduate students work on this, we've had a postdoc, etc., at the end of the day, we can dumb the data down into a geotiff, and that it's so simple to use. So we can take all of the science that's been done in universities, and at the end of the day, we can give it to a contractor and they can use it in the field, and we'll hear about that. We can give this data to Boy Scouts. So that movement of science and innovation into the hands of the people in the field is so important. We know that it's effective. We know that we've got widespread acceptance. It's exceptionally cost-effective, and there's a variety of things that you can do with it. Very quickly, some of the forest industry users. Much of this information has gone out to the forestry sector over the last couple of years to combat mountain pine beetle. We have also been sharing this data across the government of Alberta, the public service. So it's shared with Culture and Community Spirit, who use it in the historical mapping. My own department, Alberta Environment and Sustainable Resource Development. Alberta Parks, we'll hear this afternoon. They're actually one of the largest users of wet areas mapping in Alberta. The information has been shared with Alberta Geological Survey, and many of the different research organizations now in Alberta It's taught to some of the undergraduates, and we have public users now. The data was released publicly on January 14th, so there was a lot of notices that went out, but if you didn't know about it, the data that's in GeoTIFF for this green area is now available. And you can send me an email afterwards, and I'll give you the link to request the data. One of the things we really like too, though, is empowering our staff. And we'll hear about that in one of the talks after the break of how we can get this information in the hands of our field staff. And one of the comments that we hear quite commonly and have for years from people who have used this in the field is they come back and they say, now I understand how water is moving on the landscape. Because it's so difficult when you're just walking around trying to understand, is water moving this way, is it moving that way? And so that's one of the initiatives here, is really to get this information out to the land users. And in reality, that's one of the reasons we're here today. We also like to save money in our initiatives. And we're looking for ways to streamline our own internal operations and save money. And this is a really good example. This is, we were asked many years ago to map Carson-Pegasus Provincial Park, which is up near Whitecourt. And it was about 1,200 hectares. And the wet areas mapping cost the government $85. So we can't send somebody to that park and back for meal money and mileage. So we're able to do things faster, better, exceptionally cost effective. And now this is a database that the park can use and build off for many years to come. I did mention a couple of minutes ago that we do have a challenge in the false DEM. And as we move to the boreal, that problem was going to become even more evident. And we basically shut down much of our mapping activity for about 1.5 years and really tried to get a better handle on this. So we had a lot of research in the boreal forest. Much of this was supported by Statoil in Devon, as well as some other forestry companies. And essentially what we're looking at is trying to mine different attributes of the LiDAR and looking at different patterns, different attributes. And what we're really trying to do is define this boundary of wetland complexes. We're not trying to map wetlands, and this was never started to map wetlands, and LiDAR is not the best tool to actually try to do wetland classification with. But what we wanted in forestry was to know where is the boundary between operable forests and the wetland areas. And this is an example. This is north of Slave Lake. So we've got the hydrology layer currently turned on, so we've got 1 stream, 2. The orange or the red is the predicted stream channels. So these would all be ephemeral draws, and then this would be probably small intermittents. And we've got a whole bunch of probably peat bogs on this landscape. Previously, we would probably have mapped half of this is wet and half of it is dry. And now, quite different. And so we've added a separate process that's looking at the raw discrete point returns and trying to figure out where those are coming from wetland complexes and primarily peat bogs. And then that's fed back into the wet areas mapping generation. And if I go back and you just look at one of these spots, because they're very distinctive, you'll see that the boundaries line up really quite well. We want to go one step further. We want to look at the conductivity between those. So we have another graduate student up in northwestern Alberta, and this year they were all running around with hip waders, and they're looking at, one, how accurate we were with mapping these bogs. So this is the white is one of the areas where they were walking the boundaries. But really what we want to know is how they're hydrologically connected. And this question really is of paramount importance to the energy sector when we get into spills. And we'll have a presentation late in the day on that. But we see these yellow lines are where we had ephemeral draws occurring between the wetlands. And they're probably only sharing water maybe every couple of years out of a decade when it was really wet. The green area is where we have continuous flow right now, but it's very, very slow. But again, we're getting to the point where we can start mapping out those boundaries on the landscape quite well. Today is a long series of presentations to try and engage Albertans and make sure that they're aware of this technology in this innovation. So I think today is our 10th workshop, and we've done field trips. We hope that this continues in the future in engaging people. And finally, much of the work that we do is by graduate students. In fact, about 90% of the funding that we have goes to graduate students, and right now we have quite a few engaged, both at the University of New Brunswick and the University of Alberta. And their names are listed here, but it's quite a large crew, and it's growing every year.